Alright, in this video we're going to talk about linear combinations and span. This is a very important topic in linear algebra. We're going to be using this concept basically every single day from now on. So I'm going to assume that you're familiar with vectors and adding vectors and scaling vectors. So let's say that you have two vectors. Before I dive into the definition of linear combinations, let's just look at an example. Let's say that you have two vectors, u, which is 2, -3, 0, -1, and v, which is -4, 6, -2, 7. Okay, so these are two vectors in R what? What number is going to go here? 4. It's R4 because they have 4 components. And before I go on, some books will call these 4-dimensional vectors because they have 4 components, but I really don't like that because the term dimension will mean something else. Dimension describes something called a subspace or a vector space, and it's confusing if you say that this vector is 4-dimensional because that kind of clashes with the other use of the word dimension, which describes a subspace. So instead of saying a 4-dimensional vector, I'm always going to call these vectors with 4 components. I think that's less confusing than saying 4-dimensional vector. So you have these two vectors in R4. And of course, what can you do with them? You can scale them. So for instance, you can take -4v. And what's that going to be? Well, it's easy. You just multiply each component by -4. So -4 times -4 is 16. -4 times 6 is -24. -4 times -2 is 8. And then -4 times -7 is -28. So that is -4v. And what's 2u minus 3v? You want to take a moment and figure out what that is? Well, it's easy. Okay, let's just do 2u. So 2u is going to equal 4, -6, 0, -2. Oops. Minus. And then 3v is going to be -12, 18, -6, 21, right? So then this is going to equal 16, -24, -6, and -23. Okay? So these two examples, these two vectors, this vector and this vector, these vectors, okay, ooh, what am I doing? I don't even know what I'm pointing at. These two vectors, these are examples of linear combinations of these two, u and v. And how so? Well, because they're gotten by scaling u and v and then adding them together. So for instance, here, for the first one, I could get -4v by doing 0u plus -4v. Right? And here I have 2u minus 3v for the second example. So now let's talk about the general definition of linear combinations. Okay, so the general definition, ready? So if u1 through uk are vectors in Rn, so in other words, they all have n components. So it's not like you have, one vector with 2 components and then another vector with 3 components, right? They all have the same number of components. So you have k of these vectors, and c1 through ck are scalars, then c1u1 plus c2u2 plus dot 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 plus ckuk is called, so let's call this vector v. So this vector is called a linear combination of u1 through uk. So in other words, a linear combination, if you start off with these k vectors, u1 through uk, right? You start off with these vectors, you have k of them. Then a linear combination is just any vector you get by scaling these vectors and then adding up those scaled vectors. So for instance, if you have this vector 0u minus 4v, that's a linear combination of u and v. 2u minus 3v is a linear combination of u and v. I mean, any constant c1 u plus any other constant c2 times v, any vector that you can get like that is going to be a linear combination. So how many linear combinations are there? I mean, yeah, how many linear combinations of u and v are there? Well, there's zillions, because there's an infinite number of possibilities for what c1 can be, right? Just any number. And then there's an infinite number of combinations. I mean, there's an infinite number of possibilities for c2. So total, you're going to have an infinite number of linear combinations. Okay. And of course, in this case, in the example that we were talking about with u and v and R4, right, just to make sure we're clear, n is going to be 4 in this example, and this k is 2, right? So, this u would be like u1, if you want to match it up exactly with the definition, and then this v would be your u2. Okay. So it's easy to come up with linear combinations, right? If I give you these two vectors, u and v, then you can take 51u plus 2000v, and there, you just made a new linear combination. But what's harder is to tell, if you have a vector, is it a linear combination? So for instance, let's see if I can come up with a simple example. Okay, yeah. Well, before we talk about that, let's just do an example. So, example. I'm just picking problems from a textbook. So, determine if B, which is the vector 8, 9, is a linear combination of A1, which is -2, 5, and A2, which is 7, negative 3. Okay. Well, we're going to have to turn this into some sort of equation that we're trying to solve, right? So, okay, let's see if we can phrase this question without using the word linear combination. So linear combination of A1 and A2 means if you have a constant multiple of A1 plus a constant multiple of A2, right? So this question is asking, is it possible for B to equal C1A1 plus C2A2 for certain constants C1 and C2? So in other words, does this equation have a solution for C1 and C2? That's what this question is asking, right? So we just rephrase this question without using the word linear combination. In general, that's a good strategy because there's a lot of jargon and vocabulary in linear algebra. So if you can really phrase, a lot of times the hard part is just trying to figure out what the question's even asking, right? So if you can get really good and just spend some time before, just as a general strategy, before trying to think about, okay, what do I do? Before you try to figure out what to do, just try to rephrase what the question's asking and make it really clear what you're being asked to do. The question, determine if B is a linear combination of A1 and A2, is just asking, does this vector B, can it be written as C1A1 plus C2A2 for constants C1 and C2? Well, now we can see how to answer it. So basically we're trying to solve, okay, I'm going to write the C1A1 like this. So C1, so here's A1, right, plus C2A2 is 7 minus 3 equals 8, 9. And now we have to know how to rewrite this, right? How do you convert from this to a system of equations without vectors? Well, what you can do is you can multiply across. So this is, if you take a scalar multiple of this vector, right, you're just scaling each of these components. So this is going to be, how can I rewrite this? C1 times this. How can I rewrite this as a single vector? It's going to be negative 2C1 and then 5C1. Because I just multiplied each thing by C1. And then what's the second thing going to be? 7C2 and negative 3C2, right? Equals 8, 9. And now when you add vectors, you add each component. So then what equations do you get? The first component need to add up to 8. So this is negative 2C1 plus 7C2 equals 8. 5C1 minus 3C2 equals 9. And we're trying to see, does this system of equations have a solution? That's what the question's asking, right? And now this is something we know how to do. So how do we do this? You write up the augmented matrix, negative 2, 7, 8, 5, negative 3, 9. And okay, you could do the row reduction algorithm, but because the numbers are kind of annoying, it might be better to to maybe multiply the first row by 5 and the second row by 2, right? So if I do that, so the first row times 5 is going to be negative 10, 35, 40, and then the second row times 2 is going to be 10, negative 6, 18. Right? And then if I add them, I'm going to get negative 10, 35, and 40, and then 0, 29, 58. And now we can solve this, right? Because how do we write this? How do we convert this back to a system of equations? This says negative 10 C1 plus 35 C2 is 40, and then 29 C2 is 58. So then this second equation is going to give me C2 is 2, and then what's C1 going to be? Negative 10 C1 plus 70 is 40. Take away 70, negative 10 C1 is negative 30. Divide both sides, C1 is going to be 3. So we were able to solve for C2 and C1. This system does have a solution. And so what's the answer to the original question? Determine if B is a linear combination of A1 and A2. What's the answer? Yes. Because we were able to solve the system. Okay. Let's do one more example, just a little bit faster. Is 1, negative 5, negative 2 a linear combination of 2, negative 3, 1, and 0, 3, negative 3. So take a few minutes and then try to solve the problem on your own, and then we'll check answers. Okay, let's see what we get. So let's call this vector. Notice these vectors don't have a name, but we can just jump right to the augmented matrix. So these two vectors are going to go into the columns. And I'm trying to see this thing that I'm trying to see if it's a linear combination is going to go in here. Okay, so I did this kind of fast, so maybe I'll show some steps just to should I show some steps? So let's say that vector is W, and let's say that's V1, and let's say that's V2. So then this would be W is C1 times 2, negative 3, 1, plus C2 times 0, 3, negative 3. And then this would say 1, negative 5, 2, 1, negative 5, negative 2 is 2 C1 plus 0 C2, negative 3 C1 plus 3 C2, C1 minus 3 C2. And then when you write it in terms of an augmented matrix, you get that. But you know, once you get used to this, you'll see that basically you just put these vectors as the columns, and then this will be the augmented part. Alright, so now we have this. Let's see if we can solve that. So what I'm going to do, since I have an annoying 2, I'm just going to swap rows 1 and 3. So then I'm going to get I guess you don't have to, but I'm going to do it just to make it simpler. So okay. So then I'm gonna change row 2 to row 2 plus 3 row 1. So 3 row 1 is going to be 3, negative 9, negative 6. Okay. So I get this. And then I'm also going to convert row 3 to row 3 minus 2 row 1. So that will give me 0, 6, and then 5. Let me just double check the arithmetic. Yeah, I think that's right. Okay. So in our elimination process, we're done with the first column, right? Because we have this pivot, and then you have zeros down. And then what you do is you go to the next pivot here, and then move everything. So you can do row 3. You want the 6 to turn into a 0, so you can do row 3 will turn into row 2 plus row 3. So you're going to get this. Now do you see the problem? Does the system have a solution? No, because this bottom row, how do I translate that into an equation? It's going to tell me 0C1. Okay, let me just use 0C1 plus 0C2 is negative 6, and that has no solution. There's no solution for C1 and C2. So what does that tell me in terms of whether B is a linear combination, or in terms of whether W is a linear combination of V1 and V2? The answer is no. Because the system has no solutions. Right? So let's just review, when the system has no solutions, it has no solutions when you row reduce the augmented part, right? This part, you have a row of zeros at the bottom, and when you have a row of zeros, but then what did I do? Well, this is even better. And then okay. Oh. There. Okay, yeah. When the coefficient part doesn't have a 0, when it's something other than 0, then your equation is going to be 0 equals something that's not 0, and then that's going to have no solutions, right? And just to review, because a lot of students don't kind of remember this, so what happens if you have something like 0, 0, and then 0? Right? So let's say you do the augmented part, and then you get zeros on the bottom, but then you have a 0 here also. What does that mean? It doesn't mean anything, because the bottom row just says 0 equals 0. So that doesn't tell you anything, right? So if you get 0 equals 0, your system could have no solutions, but it could also have solutions. So it depends. I mean, let's say you had something like this, right? Then this would have no solutions, because it's not because of the bottom row, it's because of that row. Because this would tell you that 0 is 5, right? But let's say that instead of a 5, let's say that this was a 1 and that's a 7. Well, now this does have a solution, right? Because now, this second row, this time it will tell you that C2 is 7. 1 times C2 is 7, so C2 is 7, and then you can plug it back in to the first equation, and you're going to be able to solve for C1. So I'm just saying this as a reminder that when you do the row reduction for the augmented matrix and you have the whole thing is all zeros, that doesn't tell you anything. Okay, so in the next video we're going to continue talking about span and what that is, because I don't think we used that word yet. We just talked about how to tell whether a vector is a linear combination of other vectors.